Our next speaker is Professor Chaid Greenspan from Tel Aviv University. Chaid Greenspan is a professor of biomedical engineering in the Faculty of Engineering at Tel Aviv University. Professor Greenspan received a BA and MS degree in electrical engineering from the Technion and a PhD degree in electrical engineering from Caltech, California Institute of Technology. She was a postdoc with the CS division at UC Berkeley, following which she joined Tel Aviv University. Professor Greenspan will talk about deep learning in medical imaging, solving the data augmentation challenge for enhanced value radiology reporting.
Okay, thank you very much. So, yes, I'd like to give an overview here today about deep learning in the medical domain. And I'm also, in addition to being the head of the image processing lab at Tel Aviv University in the Faculty of Engineering, I'm also the chief scientist of a startup called RadLogix, and at the end of the talk, I'll tell you a little bit about that. Just a couple of years ago, in 2015, we were starting to ask the question if deep learning is in fact relevant for medical image domain. Today, we are asking if we're ready enough to go inside the clinics and really make a change. And this is what this talk is about. I'd like to introduce to you what we call the radiology challenge. It's one specific challenge in the medical domain. I'll then give an overview of things that we can do today with deep learning, at least things that coming out of my lab. And finally, I'd like to talk a little bit about the ability to go forward and bridge this gap between the technology we're developing and true radiology practice. So, the radiology challenge starts with the fact that in the last few years, we have been developing the machinery, the imaging acquisition systems. And we've been very good at it, so that CT machines that a few years back were getting several hundreds of slices per patient are now getting thousands of slices per patient. And then PET-CT is even more, ultrasound, and so on. We have 5 billion studies per year worldwide and growing. So imaging is definitely a very substantial component of medical practice, and we've been making it of a very high resolution. And what we've been forgetting in all of this is the radiologist. The radiologist is, in fact, the eyes that are looking at all of these scans. And we kept him way back in the past. He's actually doing the same process that he has been doing since the X-ray was invented, using his two eyes to look at the images and look for findings, some pathologies, if they are present or not. Now, this radiologist, yes. Okay, because we have increased the amount of data, of course, there's less and less time to review all of these images for the radiologist. And as a consequence of that, we are in fact seeing many missed findings, which leads to misdiagnosis, long turnaround time, which is all of us waiting to get the result of this MRI scan that we just got. And there are inconsistencies or the inability to quantify these findings, and this leads to, of course, the inability to track things over time and make things more objective rather than subjective in this whole field, in this whole domain. If we look at the output of the radiologist, in fact, the radiologist starts with a blank piece of paper, and his output is to fill that piece of paper, the radiology report. Okay, the output of the radiologist is a report. Here's an example of a report, and you see it has several parts. And if we look at the findings part, so findings, for example, you notice that the radiologist needs to look for certain injuries. This pneumothorax is air in the chest, so there's no pneumothorax. He's defining things even if they're not present. No pleural effusion, which is liquid in the lungs, and so on. Okay, and then he needs to go and check for all of these different things and identify if they're present or not. Then at the end, there's an impression or the final diagnosis or his conclusion for this patient. So if we look at the tasks that the radiologist does, they include 4 major tasks: detection, measurement, diagnosis, and reporting. Turns out that these 2 tasks take out most of his time. 80% of the time is spent on detecting and measurement, and only whatever is left is spent on the real important, critical tasks of making the final diagnosis and making a report that is substantial and usable for the referring physician. So it's definitely a place for us to put image analysis, machine learning tools to start supporting the radiologist in this process. And this is something that I've been focusing on for the last several years, and we'll get to that. But first, let's see where we are in this domain of deep learning in medical imaging, and give some examples and see how far along we are. In 2015, I told you that we just started to look at this space. 2016, we already had a special issue that came out in IEEE TMI, with a collection of the initial works coming out from different research groups. A few months later, we have a book that we published on deep learning for medical image analysis, which is further showing the amount of work that has been going into this domain. And the reason I have this arrow here is because we're now in the process of arranging for 4 different new books that will come out in the next year or so: a textbook, a handbook, and this version, another edition of this, and so on and so forth. So there's lots and lots of stuff going on, showing the amount of work that's going on in this domain. And we'll talk about a few of these examples, works in my lab on X-ray and CT. I'm not sure we'll get, due to time, to go into the MRI, but you're welcome to visit the lab page if we don't get to that. So what is really an overall challenge here in this domain is the data. So I said on the one hand there's an explosion of images, but when we're researching this space, our main challenge is the data. It's very hard to collect the data that we need. If we're looking for certain pathology, it's even more limited amount of data. And instead of having millions, we're talking about hundreds. So we're talking about hundreds. And sometimes for a specific lesion, we may have 50 cases that we can find from our hospital connections that are working with us, okay? And it's not only the data that's a problem, it's the fact that we need very high quality data. It has to be labeled by radiologists. So we need the experts to identify the data for us. This is very expensive kind of annotation, and it takes time, and many of the radiologists are not interested to do this work, especially when we're asking them to segment boundaries, and they have to do this slice by slice, very tedious and demanding kind of work. So we're dealing with this challenge in all of our projects, and I'll show you some of the ways that we have found to deal with it. In fact, this is the reason why we asked the question in 2015 if we can even do anything with deep learning, right? Because we don't have so much data. So for the last 10 years, one of the topics that has been going on in my lab is X-ray research. Okay? X-ray is in fact the simplest modality. There's a single image per patient. Why is that of interest? Well, it's of interest because it's a very, very common exam. There are 2 billion procedures a year. It's much more than CT and MRI combined. And even if I look at just at Sheba, and we see these numbers here, we see that X-ray is more than all the other modalities, and specifically within that, chest X-ray. So let me go back. Here are a few of the things that interest us in the X-ray images. This is a healthy chest. Here we see an enlarged heart situation. Pleural effusion is liquid in the lungs, and enlarged mediastinum is here. So some of these findings are very critical ones. The radiologist would be able to see them. They're evident in the image. The problem is radiologists are so busy. They prefer to look at the high-quality images that we'd like to give them now, the CTs, high-resolution MRIs, and they don't like to look at X-rays. That's a low-res kind of an image. It's a single image. It's not so interesting. Sometimes difficult to see things. Well, in the ER, we are losing lives, and I hear this all over the world, because there's not enough radiologists to look at the X-rays. So we should somehow attack and work with these images. And I formed a collaboration with Sheba, with the head of the imaging department there, Professor Eli Kunen. And for several years now, we have been collecting X-rays from his department. This is continuously being augmented. It's labeled by 2 medical experts in order to get a consensus, which is sometimes quite tricky. A sequential data, a real clinical setting means it's very difficult environment. And after a couple, 2 to 3 years, we're up to 400 cases per pathology. Okay? So what can we do with this kind of data? Well, this is what we started to look at in 2015. So we asked ourselves, can we do anything with deep learning with this kind of data? Clearly, we don't necessarily have enough to train on. So the first thing we do is transfer learning, right? Can we do transfer learning in the medical domain? So this is what we tried to do in 2015. We took a network that was trained on ImageNet and basically asked, well, if we introduce an X-ray image it's never seen before, is that still an image? Can we learn a representation from this network? And then can we use and train SVMs to identify, based on this representation, if we have a certain finding or not? If there's an enlarged heart, yes or no, mediastinum, so on, liquid, and so on. It turns out we're talking about multiple labels per case that we need, because a certain patient may have all 3 things combined. So the answer that we found, which was surprising to us in 2015, was that yes, we could in fact do the transfer learning. And we got what are considered clinically relevant results. These results become relevant clinically when they're around 85% sensitivity, 85% specificity. We always have this trade-off between wanting to get many true positives, but also we want to get few false positives. And these are the trade-offs that we see here. So these are very strong results for this set of pathologies. Since that time, we've been working more and more on addressing some pathologies which were harder for us to get, like that we have very few number of cases in to work on, and we're working on specific ones more and continuing on. But what I want to bring to your attention is that we have something very exciting that just happened in this domain. So I said I've been looking at X-rays for the last 10 years. Well, now everyone is looking at X-rays. And why is everyone looking at X-rays? Because NIH just released one of the largest publicly available data sets. So if you want to go and work on X-rays, you can. We have more than 100,000 X-ray images. And these images were just extracted from their archives in NIH, National Institute of Health. And they were annotated using natural language processing. Now that's another way of maybe treating our data problem. Just take all the data, use NLP tools to read the reports, and then we know what this data is. Well, you may ask me why I'm not doing that. The reason I haven't done this so far is because Professor Kunen has constantly told me he doesn't want to go see what his people in the department wrote in their reports. Basically, they don't really trust their own reports. Okay, so they don't trust the reports. But for us, maybe it is information. Just we have to keep in mind that it's very noisy. Okay, so the reports are noisy, but also using these tools, that's also making them annotation very noisy. It's an interesting new domain, okay? We may get to large data sets, but with very noisy labels. Now, with this kind of data, people are now trying very deep networks like ResNet, and so on. And here are some of the results that this group came up and produced for some pathologies, some that we have been looking at, some other ones. Here I'm showing you our results using the network that we've been working on so far. So, in fact, comparable and even better results. And this is all coming out in the last few months. So, definitely very exciting. We have the possibility of looking at fine-tuning now, and including localization data, and so on. So one question is how would we combine these data sets, the very noisy one, and the one that we've been trying to collect very, very carefully, and many, many issues that we'll keep on exploring. Let's shift now to CT. CT is a domain that I've been researching for a long time with the Sheba group of CT abdomen unit. And we've been looking at the process in which they analyze CT imagery, specifically focusing on the liver. And in fact, if we sit next to them, we can see that they're busy with identifying things within the liver, specifically looking for lesions. Then they need to classify these lesions. They need to identify possible malignancies, and then maybe do follow-ups. And we've been doing works on all of these. I'll show you just a few here today. So now we're talking about a segmentation task. Detection and segmentation task. You see the liver that we extract automatically on the left, and a certain lesion within the liver extracted automatically here on the right. So we introduced the use of FCNs into the segmentation of medical imagery in 2016. You see here several slices, JSON slices coming into these networks, and we're able to show on very limited data that we had to train on. You see 20 patients. For the liver segmentation, again, 20 patients, so very limited data. With these kind of masks that are given to us, we're able to get very nice results of the liver segmentation, the lesion segmentation, and we see here also quantitative results for that. Let me go forward. I want to show you another concept that we tried, which is basically looking at patches. So if we want to segment out a lesion, we can always do it as a voxel classification task. And if we want to treat data augmentation, of course, we may want to use patches, a single image, thousands and thousands of patches. That's a good way to go. So if we look at it as a collection of patches, and we want to train and learn these patches being lesion versus non-lesion, it's usually treated as a binary classification task. Okay, but we see here that within the non-lesion class, we have huge variability in these patches. And this is where I want to hint at the fact that context is very relevant to our solutions. Our solution here actually was to look at the variability within the class and identify it, and then basically split up this normal class into two, normal interior versus normal boundary. Okay, so it's a very simple decision. Basically, in order to reach this binary decision, we first classify into 3 categories, and then we'll fuse those as a follow-up step. You see also here that we introduce different scales. In the larger scale, we can see a better distinction between the lesion boundary and the liver boundary. So all of these considerations are very informative and can be crucial for our tasks. Specifically here, you'll see the difference in the false positives. In red are the false positives when we just have the 2 binary class, and then with the multi-class, we reduced a lot of these false positives. In fact, the results are even improved over the FCN in this particular run. We have very, very high true positive and only 1 false positive per case. So let me just say that clinically relevant is below 3 false positives per case. That's what the radiologist would be willing to accept. So 1 is definitely a very good place to be. Okay, and here are a few more examples. And let me run forward to a few more things that we've been doing. Let's say we want to classify these liver lesions. Okay, we detected them, we segmented them, but now we want to categorize them. Here are 3 categories. You see that we don't have a lot of data. And why are these categories interesting? Because cysts and hemangiomas are in fact benign, and metastases are malignant. For metastases, you're going to have to quickly refer to additional treatment. But metastases and hemangiomas are very similar in appearance. So the radiologists themselves have a hard time differentiating between them, distinguishing. So the question, can we use our tools to support that? So here you see a very simple network that we used on an ROI to identify one of these 3 categories. Again, the data problem is that we don't have enough data to train this kind of a network. And so we need augmentation. Now, classic augmentation, we all know. So we take the ROIs and we translate, rotate, flip, and scale, and so on and so forth. But what we're proposing here is that we do also synthetic augmentation. So let's use the GAN networks and generate more lesions. The question is, would that help us? Okay, so we have true lesions and we have the synthetic lesions that we've generated. I'll skip over the interesting experiment we did due to time, and I'll tell you the final result. So here you see another case of real versus synthetic, and here are some of our results. This is a previously state-of-the-art system. This is regular augmentation that we're all familiar with, and this is when we add to that an additional augmentation of synthetic data. And overall, in this case, we see an increase of 7%, which is very, very significant. So we are very pleased to see that with the GAN networks, synthesizing examples, we are we have capability of doing much more than we've been doing so far. And I'm taking one more step forward. We can actually now look at generating modalities. And why would we want to generate a modality? Well, here's one reason. When the radiologists try to detect a malignancy, they usually like to add to their consideration a PET image. The PET actually shows localization of malignant regions within, let's say, the liver. The entire body here, but here the liver. So this really is a supportive tool for the radiologists. But it's not always easy for us to get PET. It's even less data than the CT. So here we're generating synthetically the PET data. We're generating the PET data here synthetically using a combined network that I won't go into. You'll see here the synthesized results, very similar looking to the PET, but even more interesting for us is that we can actually use this to reduce false positives, and in fact we see a very strong true positive identification of malignancies with strong reduction in the false positives. Stuff that we're doing with the brain imagery. But what can we do now with all of this thing? Give me 3 minutes. Can we, in fact, are we ready to put this stuff in the clinic? So the classical big companies, Philips, Siemens, GE, are all shifting, of course, to deep learning. With them now are joining many new startups, and I've just collected a few. So I know that in a week's time, we'll have some more joining us. And here I want to say a few words, 2 minutes worth, about WebLogix. WebLogix, in fact, set as its goal to answer specifically this radiologist challenge that I addressed in the beginning. If we can, in fact, detect and measure to good enough accuracy, can we now support the radiologist in writing the report? So WebLogix has a zero-click workflow solution. It's integrated into the reporting system, and it's integrated into PACS, or the viewer. And these are the two screens that the radiologist is used to looking at. And basically, it extracts findings and measurements and puts them onto these two screens. So this is the viewer where the radiologist sees the images. This is the reporting system. In our case, it's Nuance. Nuance is 75% of the US market. And if we look more closely, I hope you can see some of the findings. We call this the virtual resident because some places have residents that fill in, pre-populate the report. And this is exactly what we're doing here. We're trying to start up and filling in these reports with the findings. For each finding, we can attach a key image, and we can provide measurements for the finding. So this is actually augmentation of the reports as we know it today, and hopefully saving time and making life easier for the radiologists. In addition, if we have the findings, we can put them in the work lists. So this is actually when we order the cases to look at, we can prioritize or at least hint to the fact that in some of these cases, we have found some findings. And this would help in the emergency room settings not miss some of the X-ray related findings that are currently overlooked. So how good is this? Are we really out there? Is it going to be interesting to the radiologist? Well, the study that just came out in the last few days, and it's going to be published soon, done at UCLA, has researched the scenario with and without these kind of tools. And the outcome from 3 radiologists is that they're satisfied, but even more important to us, is that we can save up to 40% of their time. Okay, so are we there? Well, 1 minute. Are we there? Hinton thinks we're there. So I didn't bring in the whole audio here of his presentation, just took out the one sentence that really caught my attention. Hinton is telling everybody people should stop training radiologists now. Okay. The only problem with him saying that is that all the radiologists were totally scared of anything to do with deep learning, machine learning, AI, and so on for a couple of years or a year. Now, slowly, people are accepting the fact that we're not going to be replacing the radiologists. We're just supporting them, giving them new tools, and redefining them, maybe, which means they'll have to do less detection and measurement and really focus more and be what we call image diagnosticians. That's going to be their new name. And for us, our challenges as engineers, always going to be the data challenge. We have to keep aware that the clinical level performance is really important to us in real settings. We need many algorithms to develop, and many more opportunities are out there. Thank you. Thank you very much.